Okay, so the next thing we're going to go over will be object-oriented programming. Which, like so many things, we do the acronym in computer software, but it's fairly common. Gets a little bit away from the acronym. I'll do that in a different color to add the S on the end. Because then we have oops, which is just a common thing to say. So you'll often hear that abbreviated just as oops. A whole lot easier to say than the big long string of words there. So going over oops, there's some definite advantages to it. There's a trade-off for those advantages, but they are well worth it. I'm going to start off with a couple pictures I always like to start off with here to get into that point. Quick rundown. It was invented back in the early 60s in Norway, the concepts, but there's an efficiency issue. We lose a lot of efficiency programming this way. But by the later half of the 1980s, computers had caught up to where computers could handle that, could handle object-oriented stuff, and it's kind of had precedence since then, because it's much, much better for humans, much, much better for us. It's not better for the machine. It's better for us as programmers to work with. And to express that, I like to start with these two pictures. This first one is going to be a picture you may have seen in biology class. If you haven't had a biology class, hopefully you're at least vaguely familiar with this, but the whole tree of life thing. We have several main branches of the tree of life, bacteria, and then a whole lot of other branches off those. Somewhere in there is E. coli. I'm just doing this kind of quick. I'm not going to spell out everything, but then another main branch. We have archaea and eukarya. And the main branches off the tree of life, and they get more specific as we go down. Like different types of eukarya might be plants and fish. Or one down here for mammals. And it gets more and more specific. A couple types of mammals. I'll just put there's obviously a bunch. I assume everybody's familiar with that. I'll just label a couple on here. Enough to point at. A couple of branches, we might have humans and elephants. A couple types of mammals. Now, hopefully you've seen that in a biology class, or it's a common enough thing. Hopefully you're at least somewhat familiar with what I'm talking about, the basic tree of life, and how humans organize and categorize all the different life forms on Earth. Kind of the natural, systematic method of categorization that works for the human mind. And I wanted to start with that, because if we diagram out an object-oriented thing, some classes that we designed to work with, when we go put that in a schematic to represent things, I'm probably going to start with the object, and we'll have a couple different examples we'll see in class. Maybe there's a car object and an animal object. That's the one we're going to kind of look at today, today's stuff. Shapes, those are common starting points. I generally alternate back and forth between these three. Big cars, the last class I taught, so back to animals this time, so that's the one we're going to look at today. But cars could, then we could get more specific. We get some properties of the car, but then we add details as we get more specific, kind of like over here. There's some properties of a mammal, but then we can get more specific and distinguish between humans and elephants by expanding and adding more properties. Same thing here, some general properties of the car. We can get more specific and talk about sports cars or minivans and different types, but details get added as we go down. It starts very general in both pictures, and we add details as we go down the chain. A couple different animals we might have. We might have a lion, which adds more details to our animal object. Or a cat. Or a dog. And again, this is jumping ahead a little. We'll come back to this. I just like to start with the pictures. So hopefully by the end of this lecture, this diagram I'm putting here will make sense. Right now, it's just kind of comparing the way programmers can do things to a way that's naturally done for humans. And then with our dog, we can get more specific, right? We could add in details and be talking about either Chihuahua or Black Lab. And just more details as we go down. And there's a couple concepts that we'll quickly preview here. We're going to talk about in detail. Encapsulation. So the things we want to say about a car, well, I'll talk about it in the general aspect over in the life form. You know, the things we want to say about a mammal, usually like has hair and a couple other properties, are going to be included here. And everything about a mammal is included in this one. And then we add details, so human will inherit all that stuff about mammals, and so will elephants, and then we'll add in more details down at this level. So it gets more specific as we go down, but everything as it follows back up kind of inherits all the traits that were used to define a more general version higher up. And then polymorphism is a word we'll use in programming, which is a big word for a simple concept. But things can act in different roles too, right? If we needed any random life form, every single thing down here could count as a life form. And that's polymorphism. If we needed any random mammal, well, in this picture we only have two choices. Either humans or elephants are the only mammals we could talk about, or generic mammal itself. But things can behave as other objects, like a human is also a mammal, which is also a eukaryote, which is also a life form in general. So we have that polymorphism, the ability of a human to behave in these different roles if we need a more generalized one. There's another case too. We'll talk about that when we get into programming. And we have the same thing over here. We're going to start defining properties and stuff. You know, different variables we can fill in to describe a mammal, different methods we can make for the behavior we would want in a program. And then we'll add layers of specificity. Add layers getting more specific as we go down. Sorry. Started trying to say a word I couldn't quite say there. Specificity. But getting more specific as we go down. And then we have, so like the dog object inherits all of those variables and methods that we defined in the animal as an animal in general. It's also available in a dog. It's also a black lab. So we have that polymorphism as well. A black lab could also behave as a dog object, which could also behave as an animal object, which could just be an object in general as well. Jumping ahead a little there, we're going to go over all this stuff in detail. I mostly wanted to start out with the pictures because you notice the diagram for object-oriented programming looks almost identical to the way that humans naturally categorize things and put them into systems. So that's the benefit of object-oriented programming. It's good for us. It works with the way humans work. We lose some efficiency doing it. That's why it was invented in the early 60s. We couldn't really do it until the mid-80s. Computers couldn't handle it until the mid-80s. And from then on, it's kind of had precedence because it works well for the human. Just completely making a couple numbers up here, but to get the idea of that, it's better for the programmer. So if the programmer can do 1,000 times more at a 10% loss in efficiency, right? The programmer can do 1,000 times more, and we're losing, 10% in efficiency, which I'm just making that number up here for this example. And we're still plus 999.9. We're still way up in the benefit area. It'd be nice if we could buy back some of that 10% and not lose so much efficiency. But it's good for the programmer, so the benefits carry through. It's worth the trade-off. But just kind of starting with these pictures is when we'll go over what all that means and make more sense in more detail. But just kind of comparing the way humans naturally do things, and now we can follow that in the way we put our programs together, great programs. And that's the big benefit of object-oriented programming, is we get to think like a human again. Okay, so starting out here, some of this is going to seem very confusing. This is a completely different way to do things. So at first, it's going to seem kind of overwhelming, very confusing, completely different, but you'll see it a few times, right? So it's something completely new, a completely, entirely, drastically different way of doing things than what you've already done. So this is going to seem a little confusing. You might think back to the very first couple days of the Introduction to Programming class, because a couple semesters ago, because our Introduction to Logic class, because it's something brand new. So it's going to seem confusing. You're going to want to see it a few times. That's why there's several classes. We're just introducing it here, kind of quickly going over the core concepts for the first view of it. In your 200 level class, you'll go in, spend a lot more time detailing it. For a lot of people, it's still going to be confusing after that. Might make a little more sense, but it takes practice. So we've already used object-oriented programming. You might not have realized that's what you were doing, but we have used it. So using it's one thing, but now we're looking at making our own objects. And we'll go over the concepts here quickly. You'll get a lot more practice at them in the 200 level class and any beyond that, and keep practicing and practicing and practicing. And really, it's going to take years of practice to get really good at this. That is what, whenever you go looking for jobs after you get your degree, you're going to see all these things that they want years of experience. And they want years of experience because it takes years to learn to create objects well. It just takes years and years of practice. It's not going to come immediately. And so remember, you're going to learn it in steps, and it's something to build up to. So some of this is going to seem a little confusing right off the bat. I'm not going over every detail. It's the introduction here. So basically be prepared for that journey of learning something. This is the main one, and when those job postings say so many, 5 years experience required, 10 years experience, that's 99% of what they want is somebody that has 10 years experience building objects, because it takes years and years and years of practice to learn to do this well. So getting started into the introduction of it, there's 3 key concepts. That we want to consider when building our objects. The first is encapsulation. Which, just the quick view of that, we're going to go over it in more detail later. The quick version is everything needed is included. So when we create an object, every data field or variable we create in every possible way to hold data that object is going to needs to be a data field built in, encapsulated. Same thing with the methods. Every method that object is going to need in order to do what we want it to do needs to be included already. We're going to go over this in more detail. So several layers of talking about these things and hearing these words again and again and again is kind of what I had in mind. Because it is a completely new thing, so it's going to take a little while to get used to it. Some of it's going to seem confusing. It's a much bigger deal in the 200 level class. You'll get a lot more practice. Hopefully it'll make a lot more sense after that. Then after whichever language you choose, then I believe the JavaScript 250 is required. You'll get more practice there. 264, the mobile app development, it's also required. You'll get more practice there. So there's lots and lots and lots of practice and refinement on this coming up. So today we're just kind of introducing it, getting started on that pathway. So encapsulation, our second key concept is going to be inheritance. And I thought for a long time when I put the notes together, what sentence did I end up with? Okay. I remember thinking for a long time when I was putting the notes together. So objects can pass attributes and methods to other objects, to subsequent objects. I just remember thinking for a long time about that sentence for the introduction level. That is different than how I say it in the 200 level when people have heard that before and have seen the overview of it. Not quite starting at the very beginning. I say that a little bit different, but inheritance, these objects can pass the attributes, data fields would be technical terms, properties is a general way to say that. The variables we're going to fill in is basically what that's doing. And methods, the functions, behaviors is the general way to say that. They can pass them to subsequent classes that are based off of each other. We already saw the quick preview of that diagram. So as we go down the thing, any attribute or method we create passes on down, and those lower ones can still use the ones going up the chain, up the tree from it. Our third key concept, polymorphism. And this is an object can behave as a different object. So if we make a car object, that doesn't mean it can only ever be used as a car object. We can do other things with it. It'll make more sense when we see it in practice, hopefully. Object can behave as another object. So an extreme example, say we make an object to, there's a better example we'll get to in a minute. An extreme example of something completely different. Say we make an object to deal with averages. We have an object has a bunch of variables and methods built into it to find averages when we give it a bunch of numbers. Well, at least one of those methods to do that is going to be add all those numbers together. Right? So we'll find an average, that add them together, divide by how many we have. So one of the methods is going to be to add those together. We could use that object anytime we wanted to add numbers. You know, if we had two numbers, we could just use that average object because it has a sum method built into it. So we could use that sum method for finding averages anytime we wanted to add. And that's an extreme case of polymorphism. We'll see some that make more sense, but the object was created to find averages, but we can use it just for regular old adding. Just using it as something, behaving as something different. So that's our three key concepts: encapsulation, inheritance, and polymorphism. And our textbook spreads this across 2 chapters. It's pretty much this one chapter on encapsulation, one chapter on inheritance. Polymorphism is just vaguely mentioned. So I wanted to kind of go over the whole spiel as an introduction. Once again, we're introducing it here. In the next class, you're going to spend a lot more time working with it, but it's going to take a while to get used to it. You're going to spend a little more time building your objects. You've already been working with object-oriented stuff, so working with it's not bad. Building good objects takes a lot of practice, though. So another point about objects is what we're going to call the open close principle. And this basically just means our objects are open for extension we can create a new, extend it into a new object, and that's where the inheritance is going to come in. So we'll be to that part in a moment. Open for extension, closed for modification. Open for extension, closed for modification. Once we create an object, it's created. It's set in stone. It's encapsulated. So we're going to start here with this part to lead into the details about encapsulation. Once we create it, it's created. It's finished. It's closed up. It's done. It's not going to be modified afterwards. It already has everything it needs. There won't be any need to modify it. So we're going to start there with the closed for modification and get into encapsulation now. Okay, so getting started here with encapsulation, and as I was erasing the board, I previewed that last video, and I kind of made a point in there. I kind of made a point in there about taking years of practice to learn to do this well. The key point there is the well. Okay, we'll be making objects here in a few minutes. Right? They are not going to be very efficient objects. They're going to be they're not going to be very efficient. Just some basic concepts here. So we'll be making objects in a few minutes. So the key point on that is doing it well. And that's why we want to get the concepts down. And something we talked about earlier, a lot of planning. The doing it well part involves a lot of planning, whether you're writing stuff down, doing it all in your head. There's a lot of thinking through on this before we get started with it. So encapsulation, that's kind of everything's included. One good example of that would be the computer itself, of working with computers. Most people that use computers have no idea how they work, right? They just know that they work. If they go do something, it's going to work. Well, for example, a key press. Do you all know how a key press works? I trust you know how to go look it up, but there's a couple different types of key presses, for one, as far as what the pieces are doing. But right off the top of your head, I'm guessing you probably don't know every single detail about how pressing the N key works, right? We just know if we push the N key, the letter N is going to show up on the screen, or we hit Control N, and a lot of software will get a new file, and we know what it does. We don't know how it does it. All the information is encapsulated. And to demonstrate the principles, I like what I call the donut picture. There's different ways to view all of this. And we kind of put our objects together like this. In our innermost circle, that's going to be our properties. Things about our object. Also called attributes. Another common thing is going to be data fields, would be a technical way to put it That's where we put our variables. They're in this inner circle, which kind of gives a layer of protection. Because in the outer circle here, that's where our behaviors go. The behaviors about the object. Methods. The methods and functions that we write that we want that object to carry out. And then that's important because, I'll draw this in another color, kind of like the key press thing, somewhere outside of our object, completely separate from it, is a client. And we don't want to give the client unrestricted access to our properties, right? They might accidentally change something important about the object. So the client has access to the behavior. Client can access behaviors. So the client can only access the behaviors we put in our object. And we could set it up so they could have access to this, but it's good form to not give the client access to this. Only let the client get to the behaviors of the objects. And then the behaviors have access to the properties and attributes, the data fields in the object. Behaviors can access properties. So that's the general idea of, the picture represents the general idea of the good form of encapsulation. We protect all our actual data. You know, that's the inner circle. The client accesses behaviors, and the behaviors have access to the properties of the object. I guess kind of like that key press example. Excuse me. We're the client pressing the key. We have access to the mechanical action of pushing the key on the keyboard. And so that's just one behavior of it, right? We can push the key and, well, it bounces back up on its own, right? So there's got to be some spring-loaded stuff in there. But that's another behavior. That's not what we're accessing. We're pushing down and letting go. And then the bouncing back up is another behavior on its own. And what the key carries out is the properties or attributes associated with that key press. So that's kind of the picture I like to get started thinking about these things. Everything's enclosed in this nice little donut, or maybe circles, because it's not an empty spot here. This inner circle is the protected stuff, the stuff we want to keep safe. So we don't give the client direct access. They have to go a roundabout way to get to the important parts, the actual data held in there. And yeah, then everything we need should be included. Or I made that comment, closed for modification. Open for extension, closed for modification. So once this is created, once we build our object here, we don't want to change it. It's, think of it like carved in stone. Another analogy I've come across that helps some people, everybody thinks a little bit different, so I try to say this in different ways, is maybe if you think about language, it might help. And think of the object as a noun. That's the noun we're going to use in a sentence. And these properties, that's every adjective or adverb we could use to describe that noun. We're not going to have any outside adjectives describing our noun. Every adjective or adverb we need is already included with that noun before we use it in the sentence. And our behaviors or methods, that's like the verbs. So everything that noun could do, the verb part, is already included with that noun before we use it in the sentence. Perhaps that analogy helps you think of it a little. I'll try to word it in different ways, just because everybody thinks a little bit different. See what works for you. And that's kind of the core idea of encapsulation. Again, introducing it here, there's a lot more to say about it later. It's a big deal in at least 3 classes to come, right? Your language specific class, then the 250 class, and the 264 class. It's going to be a big deal in there. So there's still a lot to say about it. Just introducing it here, but encapsulation, everything needs included. That's why I like that noun example, right? We're not going to use any adjectives, adverbs, or verbs that aren't already included with our noun. We already thought through every single adjective that could be used to describe our noun and put it in there before we even use it in a sentence. So everything's included, enclosed, and for good form, protected. Which you can probably already kind of picture how trying to do that, you may end up with a whole lot more than you need or miss some stuff. And that's where the years of practice comes in, right? We're already losing efficiency doing this, so we don't want to put a whole lot more than we need. And we definitely don't want to miss anything. So it takes some practice to get really, really good at it. But to just start doing it, we'll be doing it here in a few minutes. So that's the core idea of encapsulation. Next step is going to be inheritance. So the next part is the quick introduction to inheritance. There's some details with inheritance that when we summarize it are a little bit different than in practice, so we'll see that in practice, so those details work in. The idea is we can extend a fully encapsulated object into a new object that gets the behaviors and methods that's supposed to be the word "and" there, gets the behaviors and properties then adds more. This is kind of the idea in that picture. As we went down the chain, we started very general, and as we went down those trees, whether the biology one, what example of the way humans normally categorize things, or the one I previewed here of what we're working on today, as we go down the tree, we get more and more specific. We start very general, and then we add details, and more details add as we go down. And so an object will pass all its behaviors and properties onto another object, which can then add more, that's the open for extension part of that open-close principle. Open-close principle, open for extension, closed for modification. We can see this in practice. It's fairly straightforward. Yeah, most of what I have in the notes here is leading into the examples we're going to work through. And polymorphism is going to be mostly in the examples. We'll just kind of point it out a few times and show it in the examples and just kind of mention it here. The big two to start with for at the introduction level are encapsulation and inheritance. There's some technical terms. And just over the years, there's been different ways developed to say these things. Technical terms for this extension. So we could say a base class, and we'll talk about the word class in a moment. But the base class extends to a derived class. So one of the ways we can say this is a base class extends to a derived class. Another common way of expressing it is going to be superclass. So a superclass extends to make a subclass. And the third one I put down, you may come across other ways that these are said. The main point is they're interchangeable. A parent class extends to make a child class. So just different terms, but they mean the same thing. They express different ways of expressing the same extension. All three of these sets will be used in the lectures as I'm talking about this, and they're used interchangeably. I might refer to subclass and base class in the same sentence, just because I'm used to using them interchangeably. But just different terminology, but typically they go together like this. I'll try to at least keep them paired up with the one they should go. And the parent-child terminology, I guess way of saying it, is kind of nice for inheritance because it's the way that would happen in real life, right? On, the average family, or if there is such a thing as average family, parents are going to work through, have a lifelong working career, build up a life savings, and eventually the child is going to inherit the parent's life savings and then add to that what they accumulate over a lifetime working career. So we get the stuff, the child class gets the stuff from the parent class and then adds more to it. That's kind of the idea of inheritance. And we'll see polymorphism in some kind of in the examples. So let's I'm going to go ahead and erase the board. I'll step out of the way so in case you want to copy those notes down, read everything there, but just some different terminology on that side. We'll kind of start working through the example here and getting into Python specific stuff. So far all of this has been completely generalized. I'm going to try to generalize the example, but obviously we're practicing in Python, so we need to get into some Python specific stuff. So I'm going to erase the board and get into that. Okay, so kind of taking some of those diagrams to start with and putting them up here ready for the example we're going to work through when we get over to the screencasting. Up at the top, we have this thing called object, which is all objects in Python inherit from this. So using that parent-child terminology for the classes that we're going to design, we'll talk about that word specifically in a moment. But using parent-child terminology, object would be the grandfather of everything. Might be one way to think about it. So object class in Python. And so everything is going to inherit from this. So all Python objects inherit from this one. And in particular, the part that concerns us is they inherit 4 methods from this one. Really only 2 that concern us, but I didn't want to cut the list short. So 2 for this class, but I wanted to go ahead and mention the full list. Put a note here. All start and end with double underscores. So all these names start and end with underscore underscore. We'll talk about it some when we get over to the example. That does mean that is an important thing. We'll use it some as well. It's kind of an important thing. So the four methods that we're going to inherit from that, underscore underscore new, this is sort of some creation stuff. I'm just going to put do not mess with at this level. And even at a higher level, it's a really bad idea to go messing around with that. So maybe you should just say do not mess with. But it's there. The first one that's going to concern us, well, I'm going to run out of room here. First one that's going to concern us is init. And this is initialize. This is to initialize it. Everything the initialize our object, set it up, create it. So I should put something here because we usually pass stuff into that, and we set up our object. The values that we want to assign passed into the particular instance of it, or some default values. Basically set it all up in the init one. So we'll be using that one quite a bit. Yeah, I'm going to erase the board at some point. I was going to build this picture and try to list this stuff over there, but I'll move the two that we need over there. Another one that we're going to use a lot is string. So this gives the default value when our object is cast to a string. In other words, this is how we set up our default output. If we're going to print that out, print our object out, just print it out by default, what happens when we cast our object into a string. So obviously that's going to return a string. We just wanted to find what that is. And the fourth one, so we're going to use init and initialize and string. We're going to use those with our objects. I wanted to go ahead and include the list. The new method's there. Don't mess with it at this level. And really, once you've got to the higher level and have seen more about what it's going on and what it's doing, you probably don't mess with it there either. It's one of those things. It's there. We have it. But one of those things that just because we can doesn't mean we should, right? We can run full speed into a brick wall. But can and should are two entirely different things, because we should not run full speed into a brick wall, obviously. So the new method is one of those situations. What was last? Oh, equal. EQ for equal. And here we'll want to pass in some other object. This defines equality for comparisons in selection structures. So if we want to say if our object is equal to another object, we have to go in and override this method and define what equality means for our object. And in general, it's going to be a good idea to go ahead and add your own for comparison. Not just equality, but what does greater than or less than mean for your object. That way you can use it in selection structures, if blocks. define comparisons to use our object in selection structures. So this is the, well, technically still a parent, but if we use the parent-child terminology, this is like the grandfather. All objects are going to come down from, have these four methods. For us in this class, we'll want to use initialize. So obviously we want to set up our objects, and we probably want to go ahead and set up a default value. But this one you'll use a lot. That's going to be a standard as you get further along. That's when you're always going to want to override and define what equality means for your object. And you're probably going to want to add your own in afterwards. Typically a good idea to add your own, not just equality, but comparison. That way you can define what greater than or less than means when your object compares to another object. So I filled up the board really quick. So the main ones are underscore, underscore, INIT, underscore, underscore, and then we'll pass in a bunch of stuff in parentheses to initialize it. And underscore, underscore, STR for string, underscore, underscore in parentheses, and don't have to pass anything in that case. And then we define what our default output for the object will be. Those are involved everywhere. So now I'm going to erase the board, clear up some room, and then we'll build this up into an example. And I kind of cycle through some standard examples and then back to animals this time. So we'll look at some animal objects because hopefully that's something we can visualize, right? We know at least some basic things about animals and can form a picture of them in our head to help us develop understanding of object-oriented programming. Okay, so one thing that is definitely a huge advantage with the video lectures over the classroom lectures is the ability to edit. I can get to the end and be putting this stuff together and suddenly realize, wow, this is way too complicated of an example for any class that has an introduction in the title to it. So coming back a little ways, I believe I alluded to that example some. I think I'm going to just stick this in after we go over the object in Python, the object class itself, which is like, I believe I called it the grandfather, if we use the parent-child term, the grandfather object that everything else is descended for. I like to think of it that way. Technically, it is still a parent. I'm going to do a slightly simpler example that's more related to the homework stuff. One thing I wanted to note is I was kind of adjusting some of my setup, and one that I've used before that wasn't on my tablet. I installed it on the tablet and the phone, and kind of got back to using that. It's Google Keep instead of Google Task List. If you've never used this, I know I've made the point that, or had stated that kind of covered all the, was going to be done covering the notes about planning, but I thought I'd mention this because maybe this is what works best for you. Google Keep, if you've never noticed it, I guess I could have opened it already. It's the one that's kind of like a bunch of Post-it notes, if you can see that there. You have the new button to create a blank note, or I can go in one and set them up with check boxes. That's the little one over here on the side. There's two new buttons. But it's the one that's essentially like Post-it notes, is how I think of it. And while I was setting that up, I was like, maybe I could mention that briefly, because maybe that's how you work best with making plans. You know, a stack of Post-it notes, and Google Keep would be the digital version of that. Set that down there. So now getting back to objects. So we're at the introduction level. I believe I alluded to that, saying I was back to the animal example. That's one I have that covers everything thoroughly, but we're introducing objects. We don't need to be so thorough. At this point, our main thing we want to look for, we're doing object-oriented programming still. And the main thing we want to start with of our three concepts, encapsulation, inheritance, and polymorphism, is for introducing these, let's focus on encapsulation. The introduction thing, start here. And we'll keep this with our example. The homework this week is mostly about encapsulating things. So that's a good level 1 version, and then when you get in your 200 level class, then again in 250 and 264, and maybe a couple others along the way, and later for some of y'all, it's going to add up, right? And so the 200 level class, you're going to be comfortable, hopefully comfortable with the encapsulation, work on that a little bit more, and then add inheritance to it. And polymorphism, that's something we use. We don't necessarily plan for it. I described it as an object is able to behave as another object. I use that extreme case of using an average object to, anytime we needed to add numbers together, it's going to have a sum method in there. A more common one would be, I've referred to that animal example. A child can always act as its parent. So when we set up methods, set it up to expect an animal object in general, and then we can pass in a dog object or a cat object or whichever one we have in particular. So polymorphism is more something we find an object that fits our needs. We don't necessarily design our objects for polymorphism. So that's more of a usage thing. So that kind of works in along the way with using it. So let's start at level 1, just encapsulation. That's what we want to look at here to introduce it. Everything the object needs, everything about the object is included. A capsule, right? So the object is like a capsule holding things. And everything, every property or behavior that object, that describes that object for properties, or behavior, things that object can do, which is the functions and methods built into it, they're included in that capsule. Everything, it's like an independent entity is what an object is. We want to work on building those. So let's start with encapsulation and just, again, everything the object needs is included or built in. It's kind of the idea of encapsulating. Where I really learned to understand this best was when I started programming small video games. So I was able to get the syntax correct, get things working. They might not have been the most efficient objects. That better objects obviously comes with more practice, right? Very early in the lectures, I referred to the hammer as an example of a tool, right? And when you were young, somebody showed you how to use a hammer and you were able to get some nails in, right? Probably for a long time, bent more nails than actually got put in all the way. But it improved, and eventually you were, very proficient with using a hammer. Kind of making a general assumption there, but hopefully, even if you're not very good with using a hammer, the point makes sense. Working with objects is the same way. You'll be able to put some objects together. It'll do what you need, but it's going to get better as you get more and more practice with it over time. So first off, we're going to look at encapsulation, including everything we need in an object and making it its own standalone entity. So let's get started there with this new revamped example that is a lot closer to your homework assignments than the original example I had planned. I kept alluding to that animal example. So this time, let's do something that hopefully will make sense. Let's do an example of a student class. So before we start putting that together, let's talk about the word class. That's one you're going to hear a lot. A couple minutes into this, so I'm going to pause this, render the video down, and then we're going to talk about the word class, which is going to be a split second, and the video editing is done. So now that word that I've used a couple times already, class. And what this is what we're actually building. What we'll actually be making. When we say we're making objects, we're actually making classes. Because a class is a design for an object to design for an object. I guess I want to add a little bit more. I'm going to put quote marks around object. I'm going to talk more about that word as I continue on here. So it's a design for an object from which, again in quote marks, instances are created. So these two words, object and instance, when we're talking about using it in our code, that's an object or an instance of an object. So those are used interchangeably when talking about it. Those are talking terms. And that's when it's actually being used. When we're creating them, when we're building them, we're designing them, that's a class. It's very common to refer to it as a blueprint for the object, which is a great, that leads into the analogy I like to think about. I think everybody's probably familiar with subdivisions, right? We live in America, you've probably seen a subdivision or two. And it's not uncommon to see all the houses in subdivision which are all very, very similar. So let's think about that. Subdivision of, I don't know, 2-bedroom ranch homes. A typical American home. 2-bedroom ranch homes with garage, and basement. So somewhere a designer, an architect sat down and drew up a blueprint, a design, a plan for making a 2-bedroom ranch home with a garage and a basement. And then when they get to the subdivision, you make an entire subdivision, build 50 2-bedroom ranch homes with a garage and a basement. And they can all be built off that same blueprint, the same basic idea of what a 2-bedroom ranch home is. But they're going to be, each one's going to be unique as well, right? We've seen that in subdivisions. So some of them have the garage on left, others are on the right. We look at the front of the house, sometimes some of the ones in the subdivision might have the garage on the left side, some of them might have the garage on the right side, but it's still, you can still tell it's built off the same blueprint, same design. All they did was just switch the side they put the garage on. Right? Some basements are full. And some are half. I guess you have to go in the house to see that one. Can't really see that one from the outside, but some of them have a basement underneath the entire layout of the house, and some of them only part of it. That way it's still sturdier on top. but it's still basically built off the same blueprint or design. Porches, porch, front door, what else? Window trim. That list can kind of go on. The stuff we'd see immediately, it's probably going to look a little bit different on every home in that subdivision. Some of them might look the same, but there's variety in how they trim out the windows and what the front porch looks like. But it's still a 2-bedroom ranch home with a garage and a basement. It's still built off that same initial blueprint. So each house in that subdivision is an instance of the object, an instance of a 2-bedroom ranch home. And that's what instance and object refers to, the actual one that people are going to be living in. Or in our case with programming, the actual one we're using in our program. But underlying that is what we're going to be making is the blueprint for the object. And that way when we need one in a program, we'll just ask the computer to create an instance of that object from our blueprint, which is called a class, is the term we use for that. We'll design the class, and then we're ready to use it. We just ask the computer for an instance of that class. And then it'll do, these little, we'll pass in some parameters that are going to be different for each individual usage of it. But the computer will, using those parameters we pass in, the computer will construct the instance we need to use in our code. So what we set up and build is the blueprint. So that's what we're going to do in an example here in a moment. And I decided one that might make a lot more sense than the original overly complicated animal example I had that covered everything, just kind of starting with encapsulation, is a student object. Something, hopefully, well, I feel very confident that you all will be able to relate to a student object, and all the properties about students will be encapsulated in this object for us to use in other programs. We'll see that in a minute. One more thing, a little bit more talking first, and then set the design, and then we'll do the screencast on that. But a class is the design, or generally referred to as the blueprint for the object. So getting into this example we're getting ready to do, it's going to be fairly straightforward. We're going to mostly look at encapsulation, encapsulating all the data and methods that we need for a particular object. In our case, it's going to be a student object. That seems like something everybody in this class can relate to. We talked the other day, whoops, I'm going to draw that a little bit bigger. Talked the other day about the Python has this built-in class called object. And there's some internal properties to that, attributes. But in particular, the two we're going to need, I mentioned 4 because I wanted to include the whole list. I didn't want to cut that short, but there's only 2 that we're going to use in this class. And that will be the init method that will pass in the stuff we'll need to initialize our particular class, and the string method, which will define the default output for our object. So that when we say print student object, maybe print student object, Steve is an example, is a particular instance of our student class. So we'll say like print Steve, and then we want to define what the default printout is going to be. So inheriting from that, and I'm going to draw this arrow really big because this confused me for a long time. It always seemed like the arrows went the wrong way. Inheriting from that is going to be our student object, which will have some properties about a student, right? So like a student ID, a name, an address, and then some methods. We're going to look at this more formally in just a moment, but some methods the student might need. Get GPA, find GPA, some behaviors. Whoops, that's not D. Some behaviors we might want a register method to add a class to that student's list. A update grades method, different things that the programs that work with students would need all included in that object. So that when we want to write a program that works with anything about students, we already have everything we need included in that object. So we can just use it. We'll kind of look quickly at that. And we're going to spell out a little bit more formally by looking at the UML diagram. So we've talked about UML, Unified Modeling Language, the international standard of communication in IT, but programmers do a lot more international communication than other subfields of IT. So one of our pictures is class diagram, which is where we put this information. And a quick note, so obviously it's going to look like a box with some words in it. So we could draw that in all sorts of programs. You can put it right in Word, draw.io or Visio, things. There's an L one I've used a lot that's slipping my mind, but things that are used to put schematics and drawings together is going to have built-in things. So we can do it there. When we get over to the screencaster in a minute, I'm going to open up Raptor because Raptor makes some really, really, really pretty looking class diagrams. And then we can print them out easily. And in the long run, in packaging, when you're using nice IDEs like NetBeans with Java, Android Studio for doing, you'll see in the mobile app development class, and a lot of other ones, building this diagram, unlike our use case where we have to think about what's going on or the data flow, there's a lot of thinking about what's going on. This one doesn't take any thinking to draw. So most IDEs can just generate the class diagram for us. And then all we have to do is put them in a nice order. It does take some thinking to organize them nicely on the page. But it's one that we'll usually just generate. We'll just click a generate button and it'll put them all out there for us, and then we just have to figure out what a nice way to organize them. Because drawing them doesn't take any thought. But there's a couple sections. So up at the top is the identifier, which is going to be the name of the class. And then we'll have a section for properties and attributes. And then a dashed line and a section for the behaviors or methods. So obviously, if we build our classes, then the computer can just generate this for us all day long, and we just have to pick a nice order for it. To get some really nice ones, I believe everybody saw used Raptor in their SDEV 120 class. Raptor can make some really nice looking UML diagrams, so we'll look at that. And some people are visual, so flowcharts might help put stuff together there for testing. If you like using Raptor, the flowchart-based things, well, obviously if we do it in Raptor, then you can just hit generate afterwards and generate the code for it, and not have to do any typing once you get it designed. But if you like the visual-based things, then you can test it in Raptor, and when we're doing object-oriented in Raptor, we get more options of what we can do. We get a return statement at the least. But it's kind of a way to set this up, just generate it. It doesn't take any time to draw it, so the computer can draw it for us, and then we just have to organize it nicely on the page. We'll look at that, putting those together, and that's the standard way to draw that Whereas I've been drawing these donut pictures because that's the one that, from all the classes I've had, I had over programming, that's the one I thought worked the best. Dr. H over at IUS always used those. And I thought it was a really nice way to display the information, those layers of protection in those. But this would be the official one to do it. And I mentioned this arrow. It always seemed like it went the wrong way to me because we always think about inheritance. Like our object is going to inherit those methods that are listed out from the object class in Python. But the arrows, what was always confusing me is the arrows don't go with inheritance. The arrows go with polymorphism. So the arrow in the standard diagrams for these indicates that this student class that we're going to make for our example could behave polymorphic to the object class in Python itself. But we're mostly looking at the encapsulation, and then that was one that confused me for a long time, so I wanted to spell that out. The arrow points the direction of polymorphism, not the direction of inheritance. And so let's look at drawing these on Raptor and putting together the information we need for the student class, and then we'll type it up in Python for a couple quick examples, see the syntax for doing it in Python. Is that all for that? Yeah. So let's go over to the screencast and start looking at those things.